Hi there, everyone. Can you hear me? Looks like we have plenty of people for our workshop. Super excited about that. Hi there. Good to meet all of you. Yeah, I see so many people in the chat chiming in. Really great to see you all and be able to talk to you today about our quantum computing track. And we are actually going to cover some quantum computing concepts today, which will be really exciting. We're going to use this time to work up to that by first studying classical computer system and computer language, and then going to move on to quantum language. And so, yeah, it's going to be a really good time. and I'm glad y'all are here to participate. But before we get started any further, I wanted to paste in the chat our check-in link for the day. This is really important because, in order to get points for your guild, you need to check in and participate in these events. This is the only way we can tell whether you've participated. So it's important to follow that link and try and check in. And I see Imran has also posted the link, so thank you for doing that. That's nice of you to help me out with that. But yeah, I'm curious. Do any of you have some experience with quantum computing? You're free to say yes or no or a little bit. Just trying to get a sense of where people's levels are in quantum computing. You could also tell me what your level of skill is in classical computing too. Maybe you have some Python experience, which would be super helpful. I heard some random theories on YouTube. That's funny. Yeah. There's a lot of content on YouTube about quantum computing, and some say little, but it seems like most people are saying no. Newbie. No, but wanted to try it out. And yes, I once enrolled in a free quantum computing course, but never opened it. Yeah, well, that'll make sense. Okay, so it seems like most people have experience in Python, but not so much experience in quantum computing. So let's just take 10 minutes to refresh on Python. And so, that way everybody's on the same page, even if some people do not have that experience. Okay, so I think you can see my screen there. Let me go into the corner. Hopefully y'all can see now. This is just going to be a little refresher on some basic things in Python. And I'm going to go pretty fast because it seems like people already understand some Python. So this might be a little bit basic for you, but let's just try it and see how things go. So first, we can do basic operations and basic mathematical operations in Python. And so when you add 1 plus 1, you'll always get 2. These are 2 integer values in Python, which means a number that is, a whole value, no fraction between, negative and positive and 0, all integers, and you can do this operation. And also Python can store variables. So, we can assign x equals 5 and y equals 10, and that equals is assigning values of 5 and 10 to these x and y unknown variables. So we can repeat this operation, this addition operation. Let me just label this actually, because I think it's important to have some formalism. So this is addition operation. And so when we do that, we should get 15. Okay, so let's move on to basic data types. All right, so there are several data types in Python. It looks like we have some new folks joining as well. Hi there, Amit, and hello. How are you? I'm Chaudhry. Hi, how are you? It's good to see you. We're going to just do a little bit of a basic review of some data types before we get into our quantum coding workshop. Oh, and I see Wei is here too. So hi Wei, it's good to see you. Yeah, so let's keep on our review here, because I know a lot of people have some experience in Python, so I don't want to take too much time doing this. So we can assign an integer value in Python. So this is integer, basically just a number that is a whole part of a fraction. And it can go all the way from negative to 0 to positive. And we also have float values, which will basically be any kind of number that could be represented as a fraction. So we could put pi in here, but you can't put all of pi because pi is irrational, so it can't actually be stored in a float. You can store some values from pi, but you can't store all of pi. You have to kind of just store fractions. Okay, so now we're going to show a list, or I'm sorry, a string. So this is what we call string object. And this is just any sequence of characters. And so you can define a string in either this way or this way in Python. This is just the second way of defining string. And for Boolean variables in Python, we write true, or we can reassign to false. These are Boolean, and they take on the value of true or false, and nothing else. Okay, another data type in Python is what we call list. So with list, you can store a series of values, and they can be of different data types. So you see we have in this list some integers, some strings, some float, and even another list within a list. So list can store multiple data types. And we can do the same thing with a tuple. So this is what we call tuple. Finally, we have none or null data type. So here's a final one for you to think about. So those are several data types for you. Yes, good question. I thought quantum computing I started already. So before we start into quantum computing, I want to cover some Python refresher topics, because we're going to start with classical computing and then move into that. So, and also some people said they have experience in R, and maybe they don't have so much experience in Python. So not to go too much into it, but maybe we can just make sure everyone has some familiarity with Python, since the workshop is taught in Python. So here's the next portion. So Python, importantly, if you're familiar with R and not Python, then you're going to be a little bit surprised by this, but Python is a zero index language. So if you're accessing a value in a list, let's print out our list E. Oh, forgot to run that cell. You print out list E, you can see a list of values. If you type in E1, it actually prints out 2. Okay, and so that's one to go. And if you type in E0, it goes to the first one. Oh, yeah, definitely recommend the ML sessions as well. Those are super interesting. Okay, so now we will move on to list versus tuple. Now, this is something that's a little bit sort of more of an advanced topic, I guess, in Python. So if you type a list in Python and you recreate the same values with tuple, you might have wondered, why would we ever, use a tuple instead of a list? The reason is because lists can be edited, but tuples cannot. So for example, we can type print list example. And then we can actually access a value, which in this case, this is a 3. So think about which value we might change. And we'll change that value to 12, whichever one it is. You might be thinking in your head that you know the answer. If you then reprint out, we can change the value. So 3 indexes to 4 in Python, and we get 1, 2, 3, 12 as our list. But if we try to replicate this code, we just take a tuple example instead of list example, we get error. And that's because with a tuple, you cannot change the values within a tuple. And so what we say is that tuple is immutable, meaning that you cannot change the values after it's been assigned. Okay. So now let's move on to dictionaries. And dictionary is something, some people might call this hash table. And basically it's an object that's composed of keys and values. And so let's build a dictionary. We'll call it a dict object of key 1 assigned to 1 and key 2 assigned to 2. And let's print this dict object. And so the 2 keys in our project are key 1 and key 2. And the 2 values are 1 and 2. So that is how you go with that. And if you want to access a particular key, you can use the brackets to do that, and it'll print the value associated with that key. And it's important to know that dictionaries are mutable. So if we want to change the value of one of our keys, let's say we want to change key 1 to 5. Let's try to print out that. And we get 5. So dictionaries are a mutable object. All right, so now we're going to move into some statements. And these are some basic coding structures. So we have if statement. So with if statement, we type in Python, we type if and then our condition and then a colon. And then we type our action. So this is basically how we're going to do the if statement in Python. And I will give an example here from my key. So we have if x plus 4 equals 10, print apple, and else print banana. And does anybody remember what x was in our workshop? That was a pretty tough one, huh? Anyone in the chat get a extra special bonus here if you remember what x was in the beginning of the workshop? All right, well, that's okay. We'll print it out at the top. I'll print out x. You can see x was 5 from the very beginning. Well, we don't talk about her. That's really funny. That's a good joke. I like that. Yeah, it was 5. So banana would print out because x 5 plus 4 is not equal to 10. So you get this else condition. I should write a little exampler. That's another way you can do that. Okay. Now on to for and while loops. So we're going to start with a for loop. So in Python, we have this for loop concept, and you remember our E, right? Our list E. So if I wanted to print all the values of E on a new line, I can use this command because for I will iterate. Usually I is used there, kind of like this iterator, and it goes through this E list, and then we use this colon to represent what action we're going to do with that iterator. And so this little placeholder variable, we're just going to print it out. And when we do that, we get all of the values from E printed on new lines. And we also have a while loop in Python. So I'm going to give you a while loop example. So you can start with some value, let's say count equals -300, that satisfies some condition. So this is our condition here, count is less than 10. And that will cause this while loop to execute whatever's underneath here until this condition is no longer satisfied. So you can see every time we go through this while loop, I'm adding 1 to count. Actually, this is something we didn't cover yet, this plus equals, but this is an operator that basically it stands for count equals count plus 1. So that's a way to write count equals count plus 1. So we're just going to increment, and let's print out the result. See, every time we go through the loop, we get a little bit more values until eventually this condition is no longer satisfied because 9 is less than 10, but 10 is not less than 10. So we don't print out 10. Okay. So let's go on to functions. So with functions in Python, we have a function name, inputs, and then some outputs. So let's write a function. So I'm going to write the formal, well, I'm going to show you the way of writing function in Python. Yeah, this is right. Imran, that's exactly what I mean. So we can write, let's just write a quadratic function for an example. And we will give it some, basically some argument there, x. Or this is actually, I guess our function parameter is x. And we will return x squared. And so I also didn't explain this operator, but this is a squared operator. Means basically like this. 3 squared equals 3 times 3. And so when we call on this function, let's say we write t equals 5 squared. S equals my quadratic function 10. And then we want to print both of these. My quadratic function. You'll see that they work the same way, basically. Okay. And now we'll do some import statements. So I don't know if you've done an import statement before, but import statement is a way to gain additional functionality using your libraries in Python. So we'll do an import statement really quickly here. Yeah, this is a good suggestion that Imran has. So if you want to follow along on your own, you can use Google Collab or Jupyter Notebooks, and I'm gonna paste a link to this notebook so that you can follow it later on in the session. So after I'm done writing here, I'll paste a link to the key. Okay. All right. So we can do import Numpy. Numpy is a library in Python that can do numerical operations. So we'll import Numpy, and we can do numpy.sign 15. And this is going to give us the sign of a value. And we can also retrieve values from NumPy. So for example, we have numpy.py, and that will give us the value of pi. Okay. Yeah, so now I'm going to give some algorithms notes. And I think these will be important for our quantum computing lesson in particular. So let's go through these. But actually, I see in the chat that a couple of people are not really able to get this, like follow along on their own because they don't have Google Collab or Jupyter Notebook. So let me take a minute just to show how you can access Google Collab. Google Collab, I think, will be a good one for now. Okay, let's see. I'm going to paste a link to Google Collab. Oh, Imran beat me to it. So yeah, basically, let me share my screen and show you that. Thank you. Thank you for doing that, Imran. So Collab, or Collaboratory is basically just a website where you can actually do all these things that I'm doing here, but you do need to sign in with Google. But yeah, you can do all of the workshop using this website. You can import your notebooks in there, and actually, I'll give you a notebook. I'll hang on. Let me just send you a link. Okay, here we go. So there's the link to my key for this, what we're looking at right now. Okay. So, and someone wanted to go over Numpy again. So I'll scroll back up and look at that. So Santiago, here's the Numpy import statement. So we're using this import statement to gain extra features in Python. So, we have Numpy. Some people have developed Numpy and given it many features that native Python does not have. For example, this easy feature for assign, and this just convenient storage of the number pi. So there's many things that NumPy can do that are mostly focused on numerical things that native Python cannot do. So that's why we do import. And we will actually practice import statement very soon. So don't worry about getting it too down pat. All right. Now we'll move on to algorithms notes. And so no problem. So here's the algorithms notes. So algorithm basically follows this definition. You have some input, and you don't even necessarily need an input, but it goes through some algorithm and then some output. And algorithm features, one of the algorithm features is that an algorithm will follow steps. So, the algorithm is going to follow steps incrementally. And an algorithm has a start case, which is what we mean by this input. And an algorithm has a termination. So you must build these features into your algorithm. So now we're going to do a practice algorithm. And this could be one that maybe you all can follow along with, because I think it might trip up some of you, or make you think at least a little bit more about these algorithms. Or maybe it won't. Maybe everything will go very smoothly. But and maybe you'll just look at the answer key. But here's even odd. So I'm going to make a function for you called even odd, and it returns a number divided by 2, or modulo 2. So this is an algorithm because it gives an input of this number. It does this step, and then it terminates. And the terminating case is just whatever this condition evaluates to. So does anybody know what the speed of this algorithm is? In other words, how fast can this algorithm evaluate? Someone says it takes constant time for this algorithm to evaluate. Yeah. And then other people are saying it's taking linear time to evaluate. So I didn't actually really explain what are we talking about? What is this time complexity? What are we talking about with this? Well, what I'm asking is, so imagine you have two cases. Even odd 1 and even odd 1 million or 1 billion, whatever. Which one is faster? So for all of those folks who are saying constant time or O1, let's just define that. This means that both will take the same time, right? It depends on main. Yeah, I guess that's true. But okay, so actually, to be honest with you all, this first one is going to take less time. Yeah. So that both would take the same time. So you might be wondering, why is that? Why is the first one going to take more time? So this is faster and this is slower because you have to consider each case. So this number is much larger and has a different value in, let's see, how many bases? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This has 10 bases. And so you're going to have to do mathematics on all of these bases. You're going to have to reduce them all to figure out what modulo 2 of this number is. Whereas with this number, you won't have to do that. Okay. And so let me send you a link, actually. If you're interested in looking into this more, I'll send you a Stack Exchange link. But the gist of it is this has a time complexity of 0 log n. So if your algorithm has let's show what this says. So does anybody know what log of 10 is? We're saying log base 10. What's log base 10 of 10? Does anybody know? That's 1. So if we wanted to do 10, if we wanted to do even odd 10, we have to look to this to figure out. Okay, so this will take 1. So if we want to say how much faster is that than even odd of 10 to the 9th, we're going to do log 10 to the 9th. And how much is that equal to? It's equal to 9. That's right. Some folks got it in the chat there. So actually, 1 billion is going to be 9 times slower to evaluate. Now, some of you were saying 01, which means constant time. So can you think of an O1 algorithm for even odd? Does anybody have a suggestion for how we might do that in the chat? I'll give you a few seconds to think about that. Someone said add two constants, but adding is also going to take log n time, just like the modulo operation. Someone says bitwise operation, and I think if we use a bitwise operation, unfortunately, it will not take constant time because the more bits we have, the slower it will go. All right, now we have some good ideas here. So check the last bit. If it's 0, then even. If it's 1, then odd. Yeah, this is exactly what we need, this comparator operator. So let's try doing that. Find even, odd number. We're going to check the last bit, okay? And so let's go ahead and try this. So we're going to put in even, odd, and we're going to say last number equals number minus 1, which is going to take the last part of this number. I should say that we're going to use a string for this case because it'll just be easier for us to code up and for everybody to see. But this is going to take the last value of the number, and we'll return last number in 0, 2, 4, 6, 8. Okay. So when we do this now, let's say we do it with a billion. That's false, so we can just say that that's the same thing as an even number. So yeah, maybe we should call this function is odd. Actually, that might be a better name for it. But if we make a billion and one, it should say true. Well, that's a little weird. Wonder what I did wrong here. Oh, I didn't rename this. Does anybody know what I did wrong here? It's got to be some error here. So let's see. Put the last number here. Last number in there is false. Now, if we do this, that should evaluate to true. I mean, I'm not going to spend too much time on this, but well, I guess we could even just on the last number, we could do modulo 2 equals 0. Because if we do modulo 2 on a single bit, it'll be much slower. It'll be basically constant time. Oh, Fleabag is right. You have to compare with string. That's what I did wrong. Thank you. Mix that up a little bit. Yep. So now it should work. Thank you for catching that. So yes, now our algorithm works, and it will evaluate the same no matter how large this number is. It's the same amount of time. Okay. So hopefully this has convinced you a little bit of the power of thinking about algorithms a little bit, and just the amount of speed improvements that you can gain from this sort of thing. Here's one for you. Here's an algorithms question. So I would like you to guess My pin. So in US where I'm from, our bank cards, they have a pin, called your bank pin, which is 4 digits. And my bank pin is 6422. Okay. Well, it's not actually 6422, but wouldn't that be nice? But no, it's my bank pin is 6422. But I don't even want to tell you my bank pin, my real bank pin. But if you can build an algorithm to guess my bank pin, then I will tell you it. Okay. So could you design an algorithm to guess this bank pin? How would you design an algorithm that can always guess my bank pin and get it correct eventually? Someone says, "I'll trade you your bank pin back for a blahaj." That's great. um, yeah, I guess. Yeah, if someone held my money ransom for one blahaj, I guess I'd have to give them a blahaj, right? Brute force 10 to the 4 number. Yeah, this is actually the only way to do it. So let me paste in my algorithm. So this algorithm is a nested for loop. So you can see it goes through a range of 10 digits in every single domain and guesses this string composed of 4 digits. And if the guess is equal to the secret pin, it'll print it out. So it's just going to guess every single number possible. And if we run this algorithm, oh, I called it secret pin in my answer key. I guess it's a little bit nicer to call it a secret pin, but yeah, eventually it'll guess the bank pin, and so there it goes. And if I do another bank pin like 8999, it has to go through way more. Get that? In comparison, if I just happen to start out on 001, I'm really happy because it doesn't have to go through many guesses. But yeah, this is actually the only way, and we call this algorithm an exponential time algorithm. This is really bad because let's try and make my bank pin 1 digit longer. A little weird that it didn't print out. Oh, we would need to add another loop. So for m in range 10. All right, it still works, but what if we were to try a couple of our 9s in here? Be kind of slow. And then let's do another one. So now we're all the way up to 6-digit pins. That's going to take a little bit longer. See that? So if we just keep extending this, let's even just go 2 more. You'll just see how 2 more, it's just going to become unfeasible, I think. At this point, it's just going to take forever to complete. Yeah, it might eventually complete after some time, but you can see it's getting very hard. So this is exponential time algorithm. And in O notation, we call this O to the 10m. M is the length of the pin. So why are we focusing so much on algorithms? Yeah, and someone says, which one is quantum? And what are we talking about? We're talking about like classical stuff. Well, the reason why we're going through this so carefully is because quantum algorithms can often provide a huge speed benefit for computing. And so quantum technology, yeah, the idea is for quantum technology to get rid of some of these exponential time algorithms and convert them into these smaller time algorithms like constant time and log n time. So that's kind of the way to think about it. I'm going to stop this program because this one is just never going to finish. All right. And the final thing that we'll work on in this notebook is binary. So, and then we'll take a break. So let's start with binary. And I'm not sure if you all know about this, but binary is the building block of classical computers, and they encode information using either on, which is 1, or off, which is 0, in a bit. And actually, in this workshop, we'll call these classical bits because there's also quantum bits, and they don't work this same way. But let's count in base 10. Does anybody know how to count in base 10? Actually, I think basically all of you will know how to do this. So you just go through and do your normal counting. But you know, you have to recognize that every time you hit 9, there's no more after that. No more numbers. So you have to actually repeat all your numbers. And then you hit 9 again. You have to go back to 0. You just stick a 2 in front there. And you just do this forever. Now, let's count in base 5. This you might not be so familiar with. You might not even know how to do this. So in this case, we go 0, 1, 2, 3, 4. But we can't. We're out of number. We ran out of numbers in base 5. So we're going to actually go back to 0. And so this is how we count in base 5. So the number 10 in base 5 is, the number is 14, basically, 1, 4. That's how you represent 10 in base 5. Okay. Or 9, actually. 9 is 14. 10 would be 20. Sorry about that. All right, now let's count in base 2. And this is how computers count. Okay. So we get up to 1, and there's no numbers left, so we have to go back. You know, we hit 1 pretty quick. Oh, sorry, I got a little mixed up there. All right, we're hitting these numbers really quickly. So we're racking up the digits. Right, so we're just going to keep going like this. And the way that this works basically is that each of these bases has a base of 2, and the exponent is either 0 or 1. So let's practice converting a little bit from these. So convert 0 from base 2 into base 10. This is kind of easy. We can just look at the first value and say, oh, it's 0 for both of them. So 0 converts to 0. But formally speaking, what we do is we have this base 2. And this is the first, or the 0th exponent. And it's off. This is 0. So is that going to equal 0 in base 10? And let's convert 1 from base 2 base 10. Well, with 1, we have, it's basically 0, 1 in base 2. Or, well, let's just call it 1 in base 2. So we just take this, and we change the 0 to a 1. And now all of a sudden we have 1 in base 10. And any of you convert 10111 or 10110 from base 2 into base 10? Well, we'll do it together, and maybe someone in the chat can do it faster. But start off with this rightmost digit, which is 0. And that's going to be 0, 2 to the zeros. And the next one is a 1. So we'll do 1, 2 to the 1, 1, 2 to the 2, 0, 2 to the 3s. But then we have a 1, then we have a 2 to the 4. We have 1, 2 to the 4. So this number is equal to 22 in base 10. All right, it looks like Imran beat me to it by a couple seconds there. Someone says I have an impressive typing speed. Thank you. And maybe, is there a typing race, Imran, later today? Maybe I'll stop by. I don't know. I don't know if I can type abnormally fast, but okay. So, and then Imran said a Cuba has 4 options, right? And so we can go back to this binary thing. You know, qubits actually have basically infinite options. They have infinite countable options. And that's kind of a crazy concept to think about. And it's going to take us some time to really, you know, codify that and get used to it. But there was a typing race a few hours ago that I missed. Darn. But you know, we're going to work on that for the rest of the workshop. And then on Thursday, we're going to actually even do a lot more quantum computing. And actually on Thursday, we're going to access a real quantum computer. All of us are going to be able to use a real quantum computer, which we will get through IBM. And yeah, then you can say you've programmed on a quantum computer before. So that's what we're working up to. And we just starting off with some of this foundational stuff. Yeah. Yeah, next time I will come to the typing race. Yes, we're going to use IBM. We're going to use IBM's computers, and we're going to learn how to submit jobs, both using their gate notation and also using Python. So we'll use both. But for now, we're going to take a break. So I'm going to stop sharing, and I'll repost this key in case anyone wants to look at the key during the break. Oh, I just almost posted my local host hyperlink. That would be really embarrassing. There's the key again, just in case anyone wants to take a look while we're on break. Thank you, Imran. That's very helpful. And yeah, that's actually what Imran posted is a link to the whole workshop. So if you want a sneak peek on anything, if you want to get ahead during the break, that's fine. But I recommend you rest your eyes a little bit. I'm going to go make a cup of coffee. And our break will last for 10 minutes. So in 10 minutes, we will come back. Yeah. All right, folks. See you in 10 minutes. Hey there, everybody. Hope your break was super restful or recharging or whatever you chose to do with that time. I hope it was good. I chose to make some coffee, which I'm very happy about now. um, let's see what folks have been chatting about. Someone says, "Oh yeah, the Rithvi avatar kit." I know. I'm not really sure why. I don't even really know how to change the avatar in StreamYard, but yeah, um, that's pretty funny. Let's see. In high school and college, quantum gave me the most headache, and here I am in a quantum computing session. Yeah, well, um, thank you for coming. I know that a lot of people are a little intimidated by quantum, so that's why we're starting off with classical computing because I think it'll give us a good framework to start thinking about quantum computing in a productive way. Then everyone says that's teacher versus MLH. That's right. That's right. You come to MLH, boom, everything makes sense. Yeah. But anyway, so thank you all for sticking around through that break. And now we're going to work on the second notebook that I have for you, which is going to be installing Kiskit. And so let me paste that notebook into the chat. So yeah, let me go ahead and open it up for us. And again, if you want to upload, if you want to make a Google Collab notebook and do it from there. Yeah, I know my camera's vibrating. Yeah, it's not a it's a very like wobbly setup. Sorry about that. Every time I make a movement or anything, it just jiggles around. But yeah, and then Ritesh put um, a a link which is really good. This link is great. This is basically a link to the Kiskit website, and you can download a, this book in PDF format. I do believe there's a way. I'll look into it as well. But let's focus right now on what we need to be doing. So I'm going to share my screen and show you this Kiskit. And first we need to download the package, and we're going to use this thing called pip, which is a package. Oh my gosh, what does pip stand for? I always have to look it up what pip stands for. Um, but anyway, it's a package manager. And so if someone knows, put it in the chat. But we're going to use this command called pip install Kiskit. You can do this in your terminal too if you want. If you're using Google Collab or anything like that, this is probably the easiest way to do it. So we'll run that. And so that's how you install Kiskit. And after you install, it should show up on your list of installed packages. So you'll use pip list to show that. And once all that is done, yeah, here you go. It's downloading all this stuff. And so if we do pip list, it should be there. I think pip threw an error, so it might not be there, which is a little bit unfortunate. Oh, there it is. So we got Kiskit version 37.2. So you'll want to see something like that. And now we should be able to successfully import Kiskit into our code. So let's try writing a Kiskit import statement. That compiled. You can see it. compiled. So um, there you go. So folks, this is how you import Kiskit module into your Jupyter notebook. And I'm just going to linger on here for a second and see if folks can get hooked up. Yeah, it's saying I do not have the IPy Ritesh, are you using Google Collab? Or are you just using your native Python installation? Because I think if you try with Collab, the IPy kernel should be installed. And another option is just to install IPy kernel. And if you use Conda, so then you should be able to install some Kiskit stuff. All right, folks. So I'm going to finish with this notebook now and assume that you were able to successfully install with Kiskit. But if you weren't, then it should, okay, so like I said, it is working on Collab. If you weren't able to, try going to Collab, try sending a message in the chat explaining your error. You can go to Stack Exchange, stuff like that. There's a lot of ways to get this going, but trust me, it's totally possible to install this Kiskit thing. But it is a little bit tricky sometimes with all the different dependencies and environments and everything like that. So I'm going to stop sharing my screen and we'll move on to the next portion, which is going to be quantum bits. Okay. So now we're going to be moving on to quantum bits. And this is going to be where we start talking about quantum computing. This is going to be the last notebook we cover today. And then in the second workshop, we'll move on to the next 3 notebooks, which are going to be quantum states, quantum gates, and building a quantum calculator. And we're actually going to run the quantum calculator on a quantum computer. So that's going to be a really fun thing for us to do on Thursday. But for now, we'll start with quantum bits. Okay, so here we are with quantum bits. Hopefully y'all can see that page. I'll maybe try to zoom in a little bit. And so, no. And so first we're going to start by importing the Kiskit package. And to do that, you just write an import statement like we learned in the first module. And now we will move on to designing our quantum circuit. So before we do that, actually, let's talk about a classical circuit analog. This is not in the key, but I think actually maybe it would be helpful to us to just look at a classical circuit analog. So in a classical circuit, we have classical bits. So let's call it classical bit 1, classical bit 2, classical bit 3. And these values, they can take on, let's say classical bit 1 is 0, 1, 1, right? So, you know, these values are determined. And what does that mean? That means that take on a fixed value. And so determined bits are always the same when measured. When you measure C bit 1, you get 0. And then let's say you wait some time and you measure C bit 1, you're going to get 0 again. And, you know? So that's kind of what we mean by determined, that every time you measure them, they're going to show the same. Okay. So, yes, we're on quantum bits right now, Victoria. Oh, looks like we have a spammer in the chat. Don't worry, everybody. I blocked them. Okay. So now we're going to move on to designing our first quantum circuit. So these are going to so these are all registers, these 3 registers. So now we're going to make one with qubits. We call these qubits. So yeah, we call quantum bits qubits. And these 5 registers, we'll make those by using Kiskit. And so we're going to call it quantum circuit output, or QC output for short. So what this is doing is it's going to add 5 quantum bits to the front of our circuit. And I said measure, we're going to measure. Well, let's add some measurement gates to these. And let's draw them. And so QC output dot draw initial state equals true. So in this case, I'm gonna assign these 5 bits. By default, qubits are in the 0 state in Kiskit. So this will assign 5 0 state quantum bits. And you might be wondering why I wrote this bracket thing around the state instead of what I did up here, which was just parentheses. And the reason why is because this is just a way of writing quantum notation. So, this is what we call, I don't want to get too in the woods, but basically this is just a quantum representation of 0 state. And it means that 100% of the time that we measure, we should get 0. So let's draw it. Okay, so here's what Kiskit does for us. It gives us this nice drawing, which shows us, okay, quantum bit 1, 2, 3, 4, 5 all have 0 state, and then they get measured. And this measurement gate is going to transform this quantum state, which is represented by these little kets, into a classical state, which is determined. Okay, and it can be either 0 or 1. And you remember that I told you that, so let's say measurement gate transforms quantum bit into classical 1. Let's just say transforms qubit into C bit, basically, is what it's doing. And so we get our 0, and this should transform into our classical bit. This is Kiskit an app. So Kiskit is actually a library, a Python library. And let me go back. Let me send you the key for this Kiskit thing, so you can follow along, Victoria. And so, oh, this is basically how you can install Kiskit on your own. And Victoria, I don't know if you have Python installed, or if you have Jupyter Notebook specifically installed, But if you have a Google account, then you can run all of these codes on collab.research.google.com. And I just put the link to that too in the chat. So if you get started on that website, you can follow these notebooks. Which reminds me, actually, I did not post the blank notebook for workshop 3. Let me do that really quickly so that you all have the blank template to follow along to if you want. But yeah, so let's keep going. So we're transforming this qubit into a cbit. And what this ket symbol represents is that the amplitude of this zero quantum state is 1, which means that at 100%, this really means 0 times 1 state plus 1 times 0 state, meaning that there's a 100% chance of measuring 0 and a 0% chance of measuring 1 when we convert from qubit to cbit. Because remember, cbit cannot measure a quantum state. It cannot measure this ket. It can only measure 0 or 1. Okay. So what do we expect to find when we do 0, 0, 0, 0, 0, and we measure all 5? What number do we expect to get in our classical bit sequence here? Well, let's find out. So we're going to use a simulator instead of a real quantum computer because it will take less time. So I'm going to show you a simulator that we can get from Kiskit. So there's this simulator called Air Simulator. We're going to use AER to say here. Use get backend Air Simulator. That's going to be our simulator. Run this code. And we'll also have a result from this, which will be our simulator, and we'll run on the simulator. We'll run our circuit, our quantum circuit, and we'll call the results of that. And so actually in a quantum computer, we run the experiment many times because the quantum bits are probabilistic. If you remember, I said 100%, 0%. So we're going to run it many times. There's a default number of times that I forget exactly what it is. But that's why we have to retrieve the counts. So these are the counts, meaning what were the probabilities that we saw. And so I'm going to print those counts. The default is, by default, the code runs 124 times. Okay. So let's print this out. All right. So we ran our code 1,024 times, and all 1,024 times we got 0. And this is what we expect since the qubits are not modified before a measurement is taken. Okay. So we've never modified our qubits. But how will this real result change in a quantum computer compared to a classical simulator? So does anybody have a guess? Maybe if you have a guess on this answer to this question, post it in the chat. Okay, I see someone who has a question here. What is the use of quantum computers? So Santiago, there's actually no industry or commercial use cases, or even really necessarily pragmatic use cases for a quantum computer yet. There's lots of test cases where we've shown that quantum computer is exponentially faster than a classical computer. There's also problems, mathematical problems that have been solved with quantum computer that are impossible to solve with classical computer. And what I mean by that is that the amount of time it would take for a classical computer to complete the problem, even the best ones that we have on planet Earth, is tens of thousands of years. And so for those kinds of problems, it's impossible. And we've actually shown that quantum computer can do them, things that used to be impossible. But you know, there aren't really practical use cases yet. Some theories are that, you know, one of the theories is that we could use it for simulating quantum systems. So maybe you can solve the energy levels of atoms because atoms are quantum systems of, they are solved with the Schrodinger equation. So you can't simulate them with classical computer exactly, but if you use quantum computer, it might simulate exactly. And so the article says, "Oh, let me answer this here. What does it mean to take a measurement?" And Fleabag is right. It means to convert qubits to cbits, but that's a little bit of a flimsy answer. So the one that I provided to you, where I said that I transformed the qubit into a cbit. So let me try and make that a little bit more clear. So let's try and make that a little bit more clear. So basically, a quantum bit is it's a particle in the physical world. So in a classical computer, a bit is represented by basically electron state being excited or not. So if you have an excitation, then it's 1. If you don't, then it's 0. And those electron energy levels show that. And you can even use spin as well if you have like a magnetic hard drive, for example, where the spin of an atom is up or down. And so let me show maybe a Wikipedia page on spin. Um, might be a little bit easier than just using my fingers. All right, all right. Here's spin. So you can see this black arrow on this neutron, which is a small elementary particle. This arrow is representing the spin of this particle because its magnetic field is oriented in a specific way, such that the magnetic field is basically going in a clockwise direction on the left, a counterclockwise direction on the right. If you were to flip that and reverse it, then the spin would flip down. And so in a classical computer, you either have up or down spin. But you can imagine that it's possible to make this spin rotated at any direction. And in a quantum computer, we're just trying to rotate this spin to a direction where we can, not necessarily just represent 0 or 1. Okay. And so, classical bit, we can only have 1 or 0, only spin up or down. Qubit, we can have many different ones. So let's imagine that this spin was rotated a little bit, like let's say 10 degrees. Okay. Now that's a quantum state because there's no, way to represent that with zeros or ones, with a 0 or a 1. But if we measure with a C bit, most of the time it'll measure up. Some of the time, though, it might measure down because, again, it's not fully up. And that's what we're doing with this counting procedure. So with the classical bits, we're basically, let me go back to this. Classical bits, we're basically measuring 1,024 times this circuit, and we're saying, okay, well, we have this quantum bit, which is allowed to actually rotate in many different configurations. And we want to look at it on a classical bit, which is only allowed to have 1 or 0 as a value. And what will we get? And so we just run that experiment 1,000 times. We look at these, we observe these particles with their spins that are not necessarily 0 or 1, and they will resolve themselves onto these discrete determined values of 0 or 1. Okay. And so that's what we're using in quantum computer that makes it faster than our computer is we're using these quantum bits that can encode a lot more information than a classical bit. And that's really the only reason why they're better, because in for certain applications, because the bit contains more information, and therefore you can do more, a richer variety of things with that bit. Okay, so those are some ideas. Quantum bits, again, those are, if we go back to that spin example I showed you. Well, maybe there's a better example actually. The spin example, I wish I could like move it around. Yeah, okay. So the spin example that I showed you before was just up or down, right? The arrow could be up or down. But in a quantum system, we can rotate our spin in 3 dimensions. So here's a good example of that. This is what we call the Bloch sphere. And so in this sphere, our existing quantum circuit has 5 0 states. So in our existing quantum circuit, all of the spins are pointed directly up on the Bloch sphere. But we can rotate that spin by theta or phi, which are these 2 degrees of freedom in the Bloch sphere, and give it additional components. And so with those additional components, you can encode more information, and potentially when you resolve, and when we measure, we're either going to get 0 or 1. We cannot get this superposition of the multiple states. Oh, well, the way that it's created is kind of complicated. There's a lot of different methods for creating qubits. There's two different basic designs for quantum computers, and actually I think there's more now. But I don't really want to get too far into that. There's like ways of trapping atoms in lattices, or you like have a big grid of atoms and then you try to force one of them to take on a particular spin by using the lattice. And then there's other ways like supercooling. Yeah, there's all kinds of methods that people have come up with to try and particularly put these atoms into an exact rotational state, or exact spin state. But I don't want to go too far into that because I think it's a little bit not so relevant for the quantum computing coder, because the coder is gonna, the coder's not gonna really need to know a lot of that stuff. And someone said, I was a bit late, and can you give me a brief example of what is quantum computing? What is the aim here? Sure, I can definitely do that. So quantum computing is basically this idea that, we can get speed improvements on our coding, on our programs, make them faster in certain contexts by, instead of just having zeros and ones in our computer, breaking that out into having these probabilistic models. So, you can take on a range of values from 0 to 1. And instead of saying, oh, this bit is 0 and this one is 1, you can say this bit is 30% 0 and this bit is 15% 1. And so that's a lot more information that you can, a lot more possibilities um, for your bits than a classical bit allows, which just allows the two options. Okay. So, yeah, I guess I'll leave y'all with some of this stuff. It's a little bit hard to understand this. Some people have given me some good questions here, and it's kind of hard to explain these questions because we're trying not to get too far into quantum physics in this lecture and focus on the quantum computer. But for your purposes, I think it's best to think about measurement as qubit being converted to classical bit. And yeah, probability for what we are calculating. For what are we calculating? Oh, which probability? This is the probability that our qubit will be 0 or 1 when we measure it in this classical state. So let me show you here. Okay. So our qubit tells us the probability. So look at this line here. The 0 state really means 0, 1, and 1, 0. So it means 0% probability of 1 plus 100% probability of 0. So when we measure using our C bits, and every single time we measure all 1,000 times, we always get 0, then that means that the probability of getting 0 was 100. And so we can basically say that when we have this 0 state in the quantum bit, it means that we'll get a 0 in the classical bit. Now, with the classical simulators, that's ideal case. In a real quantum computer, you might not always get 0 because there will be noise. This means we are studying computer language deeply. Yeah, I mean, to understand this sort of stuff, you do have to look at the bit operations and what is a bit, because actually quantum computer is fundamentally different way of computing than classical computer. So classical computer is, only having zeros and ones at the bit level, which is the most basic level in a computer. And qubit is having basically infinite values that it can take on at the bit level, which is going to make it a lot more confusing, I think. So yeah, let me see if I can find a good article here. Yeah, maybe this is a good article. Let's see, let me read really quickly. I might leave you all with some reading for tomorrow. Just, try and let this sort of thing soak in and think about what it would mean for bits to have infinite values instead of just ones and zeros. Here's a Medium article that I just found and read over a little bit, and this seems right to me. I like the picture at the top especially, which shows that classical bit takes on just 0 or 1, but qubit can take on a range of values. So let me show that picture. Yeah. So in a classical system, you have 0 or 1. In quantum system, you can rotate among infinite options. So this top arrow is showing the 0 state, which is what we studied today. This bottom arrow is showing the 1 state, which is the same as the 0 state, but just for getting a 1 in your classical bit. And this arrow here is a superposition where both of them have equal value. So if you were to measure this right arrow, 50% of the time you will get 0, and 50% of the time you will get 1. So that's a lot of information encoded in one bit that you could never encode in a classical bit. You can never encode a 50-50 chance in a classical bit. All right, so I will leave you all with that to read, and hope you were able to learn a thing or two today, and understand why quantum computers are going to be there's an opportunity for them to be faster than classical computers in certain contexts. Glad you had a good time at the session, Imran, and yeah, I'll see y'all. Hopefully, y'all can come on Thursday when we have our second one, and we're gonna. I think it'll be more concrete because we're actually gonna build a quantum computer. And that quantum computer is we're going to build a quantum calculator, and that's going to actually be run on a real quantum computer, so you can see a little bit about what's going on with that. You should decrypt crypto. Well, actually, there's something called Shor's algorithm. I don't know if you all know about Shor's algorithm. Let me post that as well. This could be interesting reading for you. But Shor's algorithm is a really fast algorithm for solving, basically for decrypting things. So, implementing Shor's algorithm can make it easier to decrypt things like that. But all right, take care, everybody. See you next time.